What if you could bypass the stateful bottleneck that destroys most trust backends at scale? Most developers are stuck fighting OAuth 2 limitations or managing JWT complexity. But there is a more efficient path for high traffic systems. Today, I will show you exactly how to implement the grant negotiation and authorization protocol to achieve massive latency gains and rock-solid memory management that keeps your services online. We will compare the grant negotiation and authorization protocol against both JWT and OAuth 2 across 9 attack vectors, benchmark ED 25019 against RS 256 verification, and I will show you the Rust code that handles 100,000 concurrent auth requests without breaking a sweat. Let us start with the first problem. JWT, the token format everyone reached for in the 2010s. On paper it is stateless, self-contained. You verify the signature, check the expiry, and you are done. No database lookup. Sounds perfect, right? But here is the catch. JWT statelessness is also its curse. Once you issue a token, it is valid until it expires. You cannot revoke it. There is nothing to revoke, no session to delete, no database record to update. If a user logs out, if you detect credential theft, if permissions change, the old token keeps working. To revoke a JWT, you must add state back into the system. A Denylist in Redis, a token version counter in your database. But wait, that is exactly what JWT was supposed to eliminate. Now, you have a Redis lookup on every single request. You have reintroduced the bottleneck you were trying to avoid. And it gets worse. ECDSA signatures, the ones most people use for JWT tokens, are malleable. An attacker with a revoked token can derive a new valid signature for the same claims. The hash changes. Your Denylist misses it. The revoked token still works. This is not theoretical. It is in the OAuth cheat sheet as a known vulnerability. Then there is key rotation. JWT relies on JWKS endpoints and key identifiers. You publish public keys, clients cache them, and you rotate keys on a schedule. But rotation requires overlap windows, grace periods, cache TTL management. If a key identifier misses the cache, the client fetches fresh keys. An attacker can flood you with random key identifiers and DDoS your JWKS endpoint. The operational complexity is real, your JWKS endpoint. Now let us talk about the second problem, OAuth 2 with opaque tokens. This is the other approach teams use. Instead of a self-contained JWT, you issue an opaque reference token. The resource server calls the authorization server to introspect every token on every request. And that is the bottleneck. Every protected request inherits a full extra network round trip before any business logic runs. At 50 requests per second, it is invisible. At 10,000 requests per second, it is catastrophic. The introspection endpoint becomes a shared dependency every API node hammers at once. Connection pools saturate. The authorization server latency climbs. Tail latency compounds because a request now waits on the slowest of two services instead of one. When introspection latency spikes, your API gateway P99 moves in lockstep with the auth server P99. They are now the same number. So we have two broken models. JWT gives you stateless verification but impossible revocation and key rotation complexity. OAuth 2 gives you real-time revocation but a network round trip on every single request. Both buckle under high traffic. Both have killed 3 AM pages. This is where the grant negotiation and authorization protocol enters. Ratified as RFC 9635 in October 2024. The grant negotiation and authorization protocol is not an extension of OAuth 2. It is a complete redesign, and it solves both problems at once. The grant negotiation and authorization protocol is completely stateless on the server side. No introspection round trips, no database queries. But here is the core breakthrough. Every token is cryptographically bound to an asymmetric key pair. The private key stays locked in the client's secure enclave and never leaves the device. Only the public key is shared. Even if an attacker intercepts the token, it remains an inert, locked entity that cannot authorize anything without the matching. Locked entity that cannot authorize anything without the matching private key. Here is how grant negotiation works. The client generates an ED 25019 key pair locally. It sends a grant request carrying its public key to the authorization server, signed with its private key to prove ownership. The authorization server approves the request and issues a key-bound access token in a single round trip. The token can even be asymmetrically encrypted to the client public key, so only the matching private entity can open it. No redirect dance. no complex multi-step handshake. And notice a critical architectural difference: client interaction. OAuth 2 requires a web browser for the front channel redirect loop, forcing native mobile apps, desktop tools, and command line agents to spin up local web servers or embedded web views. The grant negotiation protocol handles interaction natively via back-channel API requests. The client declares its supported interaction modes directly in the JSON payload, allowing native OS passkeys, terminal codes, or asynchronous push notifications without ever launching a browser. When calling the resource server, the client presents the token along with a fresh HTTP signature created by its private key. The resource server extracts the client public key and verifies that the private key entity matches the request signature. If they match, the request executes in 50 microseconds with 0 network calls and 0 database queries. If an attacker presents that same token without the matching private key, the cryptographic check immediately fails. Let me put that in perspective. JWT verification with ES256 takes approximately 1.6 milliseconds. OAuth 2 introspection takes 20 to 200 milliseconds. Grant negotiation protocol local verification takes 0.05 milliseconds. That is 32 times faster than JWT and 400 times faster than OAuth 2 introspection. Now let us talk memory. At 100,000 concurrent requests, OAuth 2 with introspection needs roughly 10 GB of RAM just for auth state, connection pools, session tracking, introspection cache. JWT with Denylists needs roughly 400 MB. The grant negotiation protocol needs roughly 50 MB. 99.5% reduction compared to OAuth 2. But the real story is the attack surface. Let me walk you through 9 attack vectors and show you how each protocol handles them. Number 1. Distributed denial of service. OAuth 2, introspection saturates first. JWT JWKS endpoint becomes the bottleneck on key identifier misfloods. The grant negotiation protocol has no per request endpoint to saturate. The authorization server only handles grant requests, not every API call. Number 2. Resource exhaustion. OAuth 2 connection pools exhaust under load. JWT verification costs 1.6 milliseconds of CPU per request. Grant negotiation protocol verification costs 50 microseconds. 32 times less CPU means 32 times more headroom. Number 3. Man-in-the-middle token theft. With JWT and OAuth 2, tokens are bearer tokens like cash in your pocket. Whoever steals them can immediately spend them. With the grant negotiation and authorization protocol, tokens are locked safes. An attacker who intercepts the token over the wire has the safe, but they have no private key to unlock it. The stolen token is completely useless. Number 4. Cross-site scripting token theft. If malicious script steals a JWT or OAuth 2 token from browser storage, your account is compromised. But with the grant negotiation protocol, the private key is held in a protected entity that JavaScript cannot export. Even with the stolen token string, the attacker cannot sign API requests. The resource server rejects every unsigned or mismatched call. Number 5. Replay attacks. JWT tokens are replayable within the expiry window. OAuth 2 tokens are replayable but detectable via introspection. The grant negotiation protocol uses nonces in signed requests, making replays detectable even without server state. Number 6. Revocation. This is the one category where OAuth 2 wins. Real-time introspection means instant revocation. JWT cannot revoke without Denylists. The grant negotiation protocol sits in the middle. Key rotation plus short-lived tokens give bounded revocation windows. Number 7. Algorithm confusion. JWT is vulnerable to algorithm, none attacks and RS-256 to HS-256 confusion. OAuth 2 opaque tokens are not affected. The grant negotiation protocol uses ED25019 only. No algorithm negotiation means no confusion attacks. Number 8. Signature malleability. ECDSA JWT signatures are malleable. Revoked tokens can bypass Denylists. Grant negotiation and authorization protocol uses ED259 which produces non-malleable deterministic signatures. No malleability, no bypass. Number 9. Cross-site request forgery. JWT and OAuth 2 are vulnerable without state parameter validation. The grant negotiation protocol signs every request with the client private key. Cross-site request forgery is impossible without the key. The score. The grant negotiation protocol wins 8 of 9 attack categories. OAuth 2 wins 1 revocation. JWT wins 0. That is the difference between a protocol designed for 2026 and protocols designed for 2012. Now let me show you why this matters specifically for Rust. Because Rust gives us something no other language can. Zero-cost cryptographic abstractions with no garbage collector. When you write async functions in Rust, the compiler transforms them into state machines at compile time. No runtime interpreter, no dynamic allocations, no garbage collector pauses. This means grant negotiation protocol signature verification runs in approximately 50 microseconds with zero unpredictable latency spikes. Compare that to a garbage collector language. A Go service might verify in 80 microseconds but suffer a 1 to 10 millisecond garbage collector pause under load. A Java service might verify in 90 microseconds but face 5 to 50 millisecond pauses. Those pauses are what trigger 3 AM alerts. In Rust, the async thread pattern lets you define non-blocking verification at the edge. You verify grant negotiation protocol key proofs in an async handler without blocking the runtime. 100,000 concurrent verifications spread across 16 cores finish in roughly 312 milliseconds total. No pauses, no spikes, predictable latency. The ED 25019 dialect grade gives us signing in 15 microseconds and verification in 46 microseconds on modern hardware. With the AVX2 backend, verification drops to 33 microseconds. Batch verification of 96 signatures takes under 2 milliseconds. And here is the key insight. Rust ownership model means cryptographic keys are compile time safe. You cannot accidentally copy a private key to the wrong thread. You cannot leave a key reference dangling. The borrow checker enforces key lifetime safety at compile time. That is impossible in Go or Java. Let me show you what this looks like in code. A grant negotiation protocol verifier trait in Rust. You define an async verify method that takes a signature, a message, and a public key. The implementation uses ED 25019 dialect to verify locally. No network call, no database lookup, just pure computation. The resource server handler extracts the token and key proof from the request. It looks up the client public key. It verifies the signature. If valid, it processes the request. The entire auth check takes less than 100 microseconds, including serialization overhead. Now you might be thinking, this sounds great but migration sounds painful. It is not. The grant negotiation protocol and OAuth 2 can coexist in parallel. You add a grant negotiation protocol, grant endpoint alongside your existing OAuth 2 token endpoint. New clients use grant negotiation and authorization protocol. Legacy clients keep OAuth 2. Migrate gradually. For existing JWT deployments, you replace the JWKS verification with grant negotiation protocol key binding. Same ED 25019 keys, but now the token is bound to the client. You get immediate revocation through key rotation without maintaining Denylists. The long-term reliability benefit is predictable memory management. No connection pool saturation. No JWKS cache invalidation storms. No Denylist growth. When your traffic spikes at peak hours, your auth layer scales linearly with CPU, not exponentially with state. Industry adoption is in its early stages following the October 2024 RFC 9635 release. While not yet ubiquitous, the grant negotiation and authorization protocol is widely recognized as the architectural successor to OAuth 2. It solves modern distributed constraints, making it the blueprint for next-generation API security. So here is what you should do this week. First, audit your current auth layer. Are you paying the introspection tax on every request? Are you maintaining JWT Denylists that defeat the purpose of statelessness? Second, benchmark ED 25019 verification in your Rust service. The numbers will speak for themselves. Third, prototype a grant negotiation protocol grant endpoint alongside your existing auth. Let it run in shadow mode. Compare the latency and memory profiles. The data will make the decision for you. The link to the full RFC and the Rust reference implementation are in the description. I also linked the ED 25019 dialect benchmarks and the formal security analysis from ESORIX 2023. In the next video in this protocol decoded series, I will walk you through a complete grant negotiation protocol implementation in Rust, step by step, from grant request to key bound access tokens. You will have a production ready auth layer by the end. If this video gave you a new perspective on authorization, subscribe and hit the bell. Drop a comment telling me which authorization protocol you are using right now and what breaks at scale. I read every comment and I will see you in the next one.